Good morning, everybody. Can you hear me? Hello, can you hear me?
Good afternoon, Prof.
Yeah. Okay. Good afternoon to you, Delphine. You're in Kigali, right?
Yes, I am.
Okay. We've got 3 minutes. Let's wait. All right, folks, while we wait, if you have any questions from the past classes, now's the time. Any questions? Nothing? Okay, we're good.
Okay, my question is general. Can you hear me?
Yeah,
It's about the quizzes. Can we post on Piazza about the quizzes now?
sure. I mean, the quizzes, you can always ask questions, but because it's already Monday, you should be able to post on. Actually, I would
Okay.
appreciate it if you waited till tomorrow because some people have extensions, but that's only a request.
Okay, thank you.
It's 6:30 and only 75 people online. I'm missing 200 plus people. Wait 30 seconds. By the way, so since the course ad deadline is behind us, we will actually begin posting your attendance. We were a bit casual about it because there are students who are adding and dropping at this point. But now at this point, we are assuming that the roster is final, and so we can begin taking your attendance into consideration. So with that said, let's begin with today's class. We're going to continue our series of lectures on learning the network. Now, here's where we left off after the last class. We saw how learning was posed. You're given a training set of input-output pairs. So each instance consists of the input and the desired output of the network, which is the value of the actual function that you're trying to learn. And then for each of the training instances, we define a divergence between the desired output and the actual output of the network. And the divergence had some properties. What were these properties? Do you remember? What were the properties of the divergence? Anybody? So, utter silence. What were the properties of the divergence? Can someone take a guess? Someone brave. 0 for success and positive for error, right? And it was always positive. And there was a third property we wanted, which was that. What was the third property that we wanted? Anyone? Differentiable. It must be differentiable, right? And so our loss is the average divergence over the training set. And it's a function of only the network parameters, which are the weights and biases of the network. Now, I'm using some notation over here. Let me clarify. We are going to be using this notation through the course. The layers are numbered. And so the weights, when I have W subscript ij superscript 1, this 1 represents the layer index. The input is the 0th layer. Subsequent layers have layer numbers 1, 2, 3, and so on. So the superscript represents the layer index. The subscript I represents the index of the source, and the subscript J represents the index of the destination. So any connection goes from the ith node to the J of one layer to the jth node of the next layer. Now these B's, so also the superscript represents the layer index and the subscript represents the particular neuron. And also, so now, is this notation clear? It's fairly straightforward. We're going to use it. Yes or no?
Can you please come again?
Okay. So the weights you're going to be representing is W subscript ij superscript. This superscript is the index of the layer of the neuron to which we are connecting. So these are the weights for the first layer neurons. The subscripts I and J represent the source of the connection and the destination of the connection. So W subscript ij superscript 1 basically means that it's a connection from the ith node of the 0th layer to the jth node of the first layer. Similarly, Bj superscript 1 is the bias of the jth node of the first layer. Okay? Is that clear?
Yes.
Yes. Okay, please respond quickly because it's a long lecture, right? J and the superscript will not be the same. J is the index of the neuron. So for example, I can have W32 superscript 1, which means it's the connection from the third neuron of the 0th layer to the second neuron of the first layer. So the superscript 1 is the layer index. Okay. And so here's how gradient descent worked. You have this loss function, and we saw that we would initialize these parameters, the weights, and then at each step, you take a step against the gradient, which is the derivative of the loss with respect to the weights. And we'll keep iterating this until the loss converged. And now the weights, of course, this derivative is a vector of partial derivatives. The weights, W, represent all the weights in the network, all the weights and biases in the network, in fact. And so the big W is a large vector of all of these small w's, which are the individual weights of the network. And so when we perform gradient descent, here again is the loss. It's the average divergence over all the training instances. We are going to be modifying each of these individual weights by taking a step against the derivative of this loss with respect to that weight. So this is what gradient descent is all about. And it makes sense, right? We are basically checking, will increasing this weight increase the loss? If so, then you're going to decrease the weight and vice versa. And the amount by which you're going to change it is proportional to the derivative. So that means the term we now have to estimate is this guy, the derivative of the loss with respect to the weights. Now, let's look at that more carefully. The loss is the average divergence over the entire training set. So using the linearity of the derivative, the derivative of the loss with respect to any individual weight is simply going to be the average of the derivatives of the divergences for the individual training instances with respect to that same weight. So that brings us to this situation here, where we want to compute the derivative of the loss with respect to any weight, which means we want to compute the average derivative of the divergences for the individual training instances with respect to that weight. And that in turn means that this guy, this encircled term, is what we really need to be able to estimate, to compute. All this clear so far? Yes, no? Any questions? So I have 3 thumbs ups. Does that mean that our remaining 200 of you have no clue? I'll wait because we're going to use this. So maybe I can get 50 thumbs ups. I have 7. Please respond. 16, 14, 15. Are you guys paying attention at all? 21, 20. Guys, listen. If you're not paying attention, the rest of the lecture is going to go over you. When I ask you to give me a thumbs up, please do. I'll wait again. Is everything so far clear? I'll wait for those thumbs up. I'll wait for 50 of them. Can we please? Because if there aren't, then you're going to have to tell me where I lost you. 30. Guys, okay, fine. All right, so now let's go on. So this term is what we're going to compute, right? So here's where we are. We're going to begin looking. It doesn't matter. I got it all. Here is where we are going to begin taking a slight step sideways into the basic rules of calculus, right? So when for any differentiable function, I say y equals f of x, assuming x and y are scalar, and let's say the derivative is dy over dx, then we saw that the increment delta y, what this means is that for any increment delta x of x, the corresponding increment in y is given by dy over dx of delta x. We remember this, right? I can represent this using a pictorial representation. X influences y. Every time I modify x, y changes. So this is my influence diagram. X influences y. And now, on this graph, on top of the edge, I'm going to write the derivative. So this connection is going to be given a weight, which is the derivative of y with respect to x. And so what this means is that anytime I increment my x by delta x, the corresponding change in y is delta x times this edge weight, which is dy over dx. And so delta y equals dy over dx. Is this notation making sense, this picture? I'm going to be using it a lot, so is this picture making sense? All right, great. So most of you got it. So now, let's say I have a differentiable function of this kind where y is a function of many x's. What will the corresponding influence diagram look like? Anybody? What will the influence diagram look like? Anybody want to hazard a guess? Many arrows to y, right? Each of these x's is going to point to y. Beautiful. And what will the weights of each of these edges be? Anyone? Partial derivative of the y with respect to that x. And so then immediately you can see from this, what is delta y going to be? If I increment all of these x's by delta x, what will the corresponding delta y be? Anyone from this picture? It's going to be the sum, right? And so this is going to be delta x multiplied by the partial of y with respect to delta x1 multiplied by the partial of y with respect to x1 plus delta x2 times partial of y with respect to x2 and so on. So delta y is now going to be given by this formula, which is the sum of all the incoming increments over all of the edges. So this picture makes sense. And so this immediately gives me this distributed derivative rule. Now I have a nested function of this kind, okay? If I have a nested function of this kind, I have y is a function of g, where g is a function of x. So this is a nested function. When I do this, the influence diagram is going to look like this. X influences g, right? Because g is derived from x. And g influences y because y is derived from g. So this is my influence diagram. Is this picture making sense? How this translates to this figure here? Yes, okay. What will these edges contain? What will the weights on the edges be? Anybody? What are the partials, right? So this is going to be partial of y with respect to g. And this is going to be the partial of g with respect to x. In this case, it's not, there's no difference between the partial and the full derivative, so it's going to be for the full derivative. Now, I want to compute, so if I want to compute the derivative of y with respect to x, let's work this out. What is delta y in terms of delta g? This is going to be, delta y is going to be the partial of y with respect to g times delta g, right? But what is delta g in terms of delta x? What is delta g in terms of delta x? Over here. Anyone? This is going to be partial of g over x times delta x, right? So I can plug this one into this guy. And when I plug it here, I'm going to get delta y equals partial of y over g times partial of g over x times delta x. So after looking at this, what is the derivative of y with respect to x? What can you say? Just looking at this picture, this is what's written on the screen. What will it be? Anybody? It's just this product here, right? Because this is the term that multiplies delta x to give you delta y. And so you end up with a chain rule, okay? And so if this is clear, we're going to get through most of the lecture easily. And so I can say easily enough, dy over dx is dy over dg times dg over dx, which is sort of proved it, right? Now, suppose y, okay, so we're good with this. Now y, suppose y is a function of many g's, each of which is a function of x. Then what will the influence diagram look like? Anybody? What will the influence diagram look like? Anyone? A long line? What will it look like? Anybody else? X is going to go to many g's, and each of these is going to go to a y, right? It's going to look like a diamond. And so this is what it will look like. If x is going to influence many g's, and all of these g's influence the y. I'm just going to say, instead of g1, I'm going to say I use the variable z1, okay? And then what will these edges contain? The edges are going to carry the partial derivatives of y with respect to the output with respect to the input, right? So given this, what is the derivative of y with respect to x? Now, you will be able to write this, tell me this immediately, right? The derivative of y first. I can say that right here, I can say that delta y equals, because y depends on all of these guys, summation partial of y over zi times delta zi, right? But then we also have delta zi is going to be simply partial of zi over x delta x, right? And so when you combine the two, you're going to end up with this one here. Delta y is summation over all z's of the partial of y with respect to z times delta z. And each of the delta z's is the derivative of z with respect to x times delta x. Putting it all together, we find that the derivative of y with respect to x sums over all of these edges. And over each edge, it's the derivative of y with respect to z times the derivative of z with respect to x. You'd sum it over all incoming edges. So is this making sense, this picture? Yes or no? Right. So it's a very nice, pretty way of looking at things, right? And so we will use that. And so for any nested function, if I have L equals f of y, dl over, where y equals g of z, then dl over dz is dl over dy times dy over dz. And for something of this kind, where f is a function of, L is a function of many z's, where each of them is a function of a common x, then the derivative of L with respect to x is going to be the sum over all z's of the derivative of L with respect to z times the derivative of z with respect to x. Easy, okay? And so first calculus lesson. We'll have more. So now how do I compute the derivative of the divergence for any individual training instance with respect to any network parameter? For this, before we do that, we'll have our first poll. And let me release this. Can you folks see the poll? Okay, 10 seconds. All right, let me end the poll. Here's what you guys thought. Stop sharing, go back. And okay, first statement, true or false? The first statement, true or false? True, okay. Second one is the first statement, is it true? The second statement, also true, right? Is it true? Second statement is false, okay. The derivative of the influence variable with respect to the second, all of them are true. The derivative of the influence variable with respect to the influencer must be summed over all outgoing paths from the influencer variable. Basically, you have to sum over all outgoing paths to the influenced variable. Anyway, so let's go back and look at the network. So here I'm going to use a short, tiny two input network for illustration for the rest of my explanation. But then within each perceptron, we actually have two operations happening. First, we compute a weighted sum of all of the inputs. I'm not explicitly showing a bias. Instead of a bias, I have an extra value pegged at 1 to account for the bias, like I explained in the last class. And so first, we're going to compute a weighted sum of the inputs, and then you put that through an activation, right? So this affine terms, and I've explicitly shown all the weights over here. The W0s are the biases. Now, what happens? The first thing you compute is this affine term for each neuron. The affine term is the weighted sum of all inputs plus the bias, right? So the affine term is going to be, Aditya, post that on the on Piazza, and I will reply. So the affine term over here, again, Z1 superscript 1 says that it's the affine value for the first neuron of the first layer. So this Z2 superscript 1 is the affine value for the second neuron of the first layer. The output of the activation I'm labeling as Y. So Y1 superscript 1 says it's the output of the first neuron in the first layer. This is the output of the second neuron in the first layer, and so on. In each case, the superscript is the layer index and the subscript is the neuron index. This notation clear to everybody? Okay. So now, again, Delphine, the superscript is the index of the neuron, the subscript is the index of the neuron, the superscript is the index of the layer. First, so we want to compute the derivative of the divergence with respect to some weight, say this guy, right? But then, if I want to compute the derivative of the divergence with respect to this one, we know from our earlier discussion that when I have a function, the value of the derivative depends on where I compute it at. At different locations, the derivative can be very different. And so in order to get the information about where we are computing the derivative, we will need all of these highlighted terms, which are the intermediate variables in the network. And those must be used to compute the derivative. And that's where we will compute the derivative. So the first thing we will do is to compute all of these intermediate terms. That's what we will call the forward pass. So in the forward pass, you pass in the input, and then you pass it all the way through the network and compute the output of the network. So the information is going forward through the network. That's why it's the forward pass. How is it computed? This is basically the same as inference. And so how is it computed? Here's how it is. For notational simplicity, I'm going to represent the input as the 0th layer. So y subscript I superscript 0 simply represents the input. And the bias is represented as the weight of the 0th element in each layer, just for notation, okay? So what happens in my forward pass? We first compute, starting from the input, we first compute the affine values at each of the neurons in the first layer. So what is the affine value of the first neuron in the first layer? The affine value is simply the weighted sum of all of the inputs, where each of these edges has its own weight. So Z1 superscript 1, which is the affine value for the first neuron of the first layer, is the sum over all inputs. The bias is being subsumed by this value, this 1 over here. I added an extra component, which I fixed at 1, and its weight becomes the bias, just for the illustration, right? So I'm summing over all of the inputs, and I'm going to be multiplying the weight I'm going to be multiplying the input by the weight of the corresponding connection. And so that's going to be y1 times w11 plus y2 times w12 and so on. And this sum will give me my affine value for the first neuron. Fairly straightforward, not complex. I can do the same computation for all of the neurons in the first layer. And so this simple weighted summing of inputs is going to give me the affine values for all the neurons. Once I compute the affine value, I can put each of these affine values through the corresponding activation, and then I get the outputs of the neurons, all the neurons in the first layer. So the output of the jth neuron, yj, is simply the activation function of the first layer applied to the affine value zj. And now I will have the outputs of all the neurons in the first layer. From those, I can take a step forward and use the same weighted sum equation to compute the affine values for all the neurons in the second layer. And now those affine terms can be put through their corresponding activations to get the outputs of the neurons in the second layer, and so on. I can keep doing this all the way to the end of the network. So did this computation make sense? What we just did? It's fairly straightforward.
I have a question. I'm seeing this notation where W has the second subscript is corresponding to the next neuron, like
The destination
C
neuron,
subscript.
yeah.
So how is that? How does that make sense with when we do matrix multiplication and it's the row of the weight which defines which neuron gets?
We are just speaking at this point element by element, okay? We will get to that later, okay? All right. So again, Hang, this 1 over here, I just put in an extra 1 in every layer, and its weight becomes the bias, that's all, okay? So this forward computation, if I just write a simple pseudocode for it, I'm going to iterate through all the layers. I just set the 0th layer to the input. And then for each input, within each layer, I'm going down the neurons. And for each neuron, I first compute an affine value. And then I put that affine value through an activation to get the output of the neuron, the outputs of that layer. And I can keep doing this till I get to the final output. And so this simple iteration will perform inference. It will perform the forward pass for the input. So I have some pseudocode over here. You set y0 to be the input. Then you go through the layers. Within each layer, you go through the neurons. And for each neuron, you compute the affine value and pass the affine value through the activation to get the output. The output of the final layer is the output of the network itself. So at this point, we have computed all the intermediate values and the output of the network. These are supposed to be, must be remembered. Then, since we are training, for the input, there will be a desired output. And we can compare the output of the network with the desired output and we will get a divergence. Now, once we have a divergence, remember our divergence function is differentiable, right? We will use this, having computed the divergence, now we can go back and compute the derivative of the divergence with respect to all the elements in the network. And the way we will do it, first, we will compute the derivative of the divergence with respect to the output of the network itself. And this we know how to compute because the divergence function is something that we devise. And so I'm going to assume that we know how to compute the derivative of the divergence with respect to the y values which go into the divergence function. Subsequently, from here, I can take a step back. Basically, what the derivative over here tells me is how much perturbing this y perturbs the divergence. Next, I'm going to go take a step back and figure out how much perturbing this z perturbs divergence. And the way we will do it, we'll see how much does perturbing z perturb y. And we've already seen how much perturbing y perturbs the divergence. So if you combine the two, you're going to find how perturbing z perturbs the divergence. And then having computed the derivatives for these z's, we will take a step back and compute the derivatives of the divergence with respect to all of these weights, the weights of all of these connections. Then take a step back and take the derivatives with respect to these y's. Then take a step back and take a derivative with respect to all of these z's, and so on till we go back all the way to the beginning. You can even eventually compute the derivative of the divergence with respect to the input itself. Now, why do we have to go backwards? Can someone tell me for this? Yeah, all the parameters and all the intermediate variables. So the chain, okay, here is it's not just, yes, it's a chain rule, but here is how it is, right? Consider the z, right? When I'm computing the derivative of the divergence with respect to z, what I'm really asking is how much does perturbing z perturb the divergence, right? But then z perturbs y, and y perturbs the divergence, right? So first, we have to say how much does perturbing y perturb the divergence? And then how much does perturbing z perturb y? And then you can combine the two. So you need to know how much perturbing y perturbs the divergence before you can compute how much perturbing z perturbs the divergence, which is why we have to go backwards. You always need the derivatives ahead of you in order to compute the derivative for any variable. Did that make sense? Yes, no? Right. So, okay, maybe half a dozen yeses. I'll go with half a dozen. That makes sense, guys? Okay, right. And so let's see the math. The math is very straightforward, okay? Again, here's a network. I'm assuming that I have the derivative of the divergence with respect to all the outputs of the network. So I have the derivative of the divergence with respect to these y, the output of the final layer. Then I'm going to apply my chain rule. If I have L equals f of y, then and y equals g of z. Remember, this loss is a function of y, but y is a function of z, right? So if I have L equals f of y where y equals g of z, then we know that dl over dz is dl over dy times dy over dz. That's just this chain rule, right? Z influences y influences L. So when I plug it in here, the derivative of this divergence with respect to this z is going to be the derivative of this divergence with respect to this y times the derivative of y with respect to z. And the derivative of the divergence with respect to y is something that we have already computed. We assume we have it. What is the derivative of y with respect to z? Anybody? What is the derivative of y with respect to z? Yeah. What would it be? Anyone? Anybody want to answer this question? It's just going to be the derivative of this activation function at the current value of the z, right? And the z, of course, has been computed in the forward pass. And so I can replace this dy over dz by the derivative of the activation function. Simple enough. And at this point, I have the derivatives for all of these z's. Next, I'm going to compute the derivative of the divergence with respect to the weight of the connections going into these z's, which is the derivative of the divergence with respect to wij's for the nth layer. But the derivative of the divergence with respect to this weight is simply the derivative of the divergence with respect to z times the derivative of z with respect to the weight. That's just the chain rule as before, right? And of these terms, which term have we already computed? Of these two terms, which have we already computed, guys? We already have this guy, right? We just computed it, right? And what is dz over dw? What is this term? Anyone? Here. We know that z is the summation over all of these guys of y times w, right? So this z is this wy times this w plus a bunch of other terms. So the derivative of this z with respect to this w is simply going to be the input y. And so this making sense? The derivative of the divergence with respect to any weight. So again, this z is this y times this w plus this y times this w plus this y times this w and so on, right? And so these other terms don't involve this w. So I'm just writing it as other terms. So the derivative of z with respect to w is simply going to be y, right here from this one. That answer your question, Aza? Over here? Okay. And so I can just replace dz over dy, dw by this y, which I have computed in the forward pass. And so the derivative of this divergence with respect to, there are no other terms. So the other terms over here, this one, that is, yeah, it's this guy times this, that's this term here, plus this guy times this, plus this guy times this, plus this guy times this, but none of them involve this particular w. So I've just grouped them as other terms. That answer your question, Mayur? Okay, so continuing. And so I can replace this dz over dw by y. And so here we have it. The derivative of the divergence with respect to this w is the derivative of the divergence with respect to the z times the y. So for any connection, the derivative with respect to the weight is the derivative of the divergence with respect to z times the input. And we will see more, right? So, and for the bias term, of course, y is 1. The next thing we will use is this distributed chain rule. If you have some x which influences many z's, and all of these z's influence L, then we know the derivative of L with respect to x has got to sum over all of these connections. And so the next thing I want to compute is the derivative of this divergence with respect to this y. But this y influences both of these z's. And both of these z's in turn influence the divergence. So if I want the derivative of the divergence with respect to this y, I must sum the derivative of the divergence with respect to this z times the derivative of z with respect to y plus the derivative of the divergence with respect to this z times the derivative of this z with respect to this y. So I have to sum over all z's, and I have to the term I will be summing is the product of the derivative of the divergence with respect to z and times the derivative of z with respect to y. Is this making sense to all of you guys? This is just a simple distributed chain rule, right? And can you simplify this for me? This term we've already computed, right? What is derivative of z with respect to y? Over here. Anyone? It's, again, remember, z equals wy plus other terms, right? So the derivative of z with respect to y is simply going to be this weight. So the derivative of this z with respect to this y is going to be this weight. The derivative of this z with respect to this y is going to be this weight. And so I can just replace these guys by the weight. And so there I have it, right? I can use the same formula to compute the derivatives for all of these y's. And so the derivative of the divergence with respect to each of these y's is the sum over all z's of the derivative of the divergence with respect to z times the weight. It's a weighted sum of the derivatives for the z values. And so here, I've now computed the derivative with respect to these y's, these z's, all of these weights, and finally these y's, right? Again, Mayur, the bias term, you don't need to compute a derivative with respect to the bias term. It's fixed, it's just 1, right? For there, you only need the weight. You could compute it, you're never going to use it. Now, having computed the derivatives with respect to these y's, I can take a step back and now use the same chain rule to compute the derivative with respect to these z's by multiplying the derivative for y by the derivative for the activation function. Then I can take another step back and compute the derivatives for all of these weights. And the derivative for any weight, again, is the derivative for the divergence with respect to the z times the corresponding input y, right? Where for the y is 1. And then I can take a step back and compute the derivatives using the same formula. The weighted sum of the derivatives for all of these z's is going to give me the derivative of the divergence with respect to these y's for all the y's here. And then I can take a first step further back and compute the derivatives for all of these z's and keep going back until I can until I get derivatives for all the variables, including weights, biases, and intermediate terms in the network. Did this simple procedure make sense? Right? Yes, no, guys. Can you give me some thumbs up, like 50 of those? It's very straightforward. Okay. And so here is the backprop. Very simple, right? I'm assuming the forward propagation is already done. And so I'm going to first initialize the derivative with the derivative of the divergence with respect to these y's. Then multiply those with the derivative of the activation function to get the derivatives with respect to these z's. Then I keep going backwards. The derivative of the divergence with respect to the y's is simply the weighted sum of the derivatives for these z's. The derivative of the divergence with respect to the z is simply the derivative for y multiplied by the derivative for the activation. And off to the side, the derivative for any weight is going to be the product of the derivative of the divergence with respect to z times the corresponding y. So very simple pseudocode, which I've actually also written in pseudocode form. Now, if you look very carefully, this is what the pseudocode looks like, right? Instead of writing dy, partial divergence with z, I'm going to write this. I'm going to use a different notation, and this looks a lot like the forward pass. Look at this, right? First, we are computing a weighted sum of the derivatives in the next layer, and then you're passing it through the derivative of the activation. So in the forward pass, you first computed a weighted sum and then passed it through an activation, right? In the backward pass, we are doing the same thing. We are doing a weighted sum of the derivatives in the next layer and then passing it through an activation. The only one extra term is the derivatives for the weighted sum. And so it turns out that the code that you use for the forward pass is very analogous to the code that you would use for the backward pass, right? So that makes sense to everybody so far? If not, here, let me launch the second poll. Can you see the poll? Yeah. Okay. So I'll answer that, Maitri. Just give me a second. You guys have 5 seconds for this poll. All right, let me stop this. Here's what you guys thought. Back, okay. Which of these statements is true? Only 3, right? So this whole business of computing your derivatives going backward, this is what we call backpropagation. It's called backpropagation because we keep propagating the derivatives backward. But backpropagation is the process of computing derivatives. It's not a training algorithm. Backpropagation is only used to compute derivatives. And these derivatives will be plugged into the gradient descent rule for the actual training. And Maitri over here, which eye are you speaking of? You're going down. So here's what we do. As I go back, at each layer, I'm going to go down all of the neurons within the layer. And so the eye over here is the index of the neurons within the layer for which we are computing the derivatives. That makes sense? Gayatri? Okay, so yeah. Is no, backpropagation is strictly the process of computing derivatives. If I want to compute the derivative of this divergence with respect to any weight, I've got to propagate derivatives all the way backward till I compute this derivative. So it's a backpropagation is the algorithm for computing derivatives. Once you compute derivatives, you will use those derivatives in the gradient descent algorithm for training. So Delphine, this is all about computing derivatives. We're not speaking of minimizing errors at this point, okay? So now in the discussion so far, we have assumed that the computation of the output of one neuron does not directly affect the outputs of the other neurons. Each neuron is individual, right? We've computed that the inputs to the neurons are basically weighted sums. This affine term is the weighted sum of inputs. And we've assumed that the activations are differentiable. We made 3 assumptions. And implicitly, I snuck them past you. Let's examine them and see if things can be different. So consider this business of vector activations. In the simple model I just showed, you'd compute these affine terms for all neurons and then pass each affine term individually through an activation. So if this affine term changed, only this y would change. The remaining y's would not change. But then you can have vector activations where changing this one z could change all of the y's. We actually mentioned an example in the previous class. Which was it? An example of a vector activation. Anyone? Softmax, right? And so what happens is, in a scalar activation, modifying a z only modifies the corresponding y. In the vector activation, you have to think of a vector of inputs going in and a vector of outputs coming out. And so when I draw the influence diagram, in the scalar activation case, each z only influences the corresponding y. In the vector activation case, each z influences every y. The influence diagram becomes more complex. So this changes the way in which we compute derivatives. Now here, in the scalar activation case, if I have a divergence d, each of these y's is going to be influencing the divergence d. But then, if I want to compute the derivative of the divergence with respect to this z, I just have to go past this one line. This is the only connection between d and z. So that's enough for me to say the derivative of the divergence with respect to this z is the derivative of the divergence with respect to this y times the derivative of y with respect to this z. It's a very simple, straightforward computation, right? For this simple case. But then if I have something of this kind, where the z influences all the y's, then each of these y's in turn influences the d, right? So here, if I want to compute the derivative of the divergence d with respect to the z, I have to follow all of these paths. So this derivative of the divergence with respect to the z is going to be the derivative of this divergence with respect to y times derivative of y dy over dz plus the derivative of the divergence with respect to this y times this dy over dz and so on. I'd have to sum over all paths. And so now in this case, in the vector activation case, when I want to compute the derivative of the divergence with respect to any z, I must sum over all of the outputs of the layer. And the terms I will sum are these guys, the products of the derivative of the divergence with respect to the y times the derivative of y with respect to z. Is this making sense? Everybody over here? Okay. And specifically for the softmax case, this is the softmax, right? Where you exponentiate each z and then you normalize it. Here, what do you think the derivative of y with respect to z will be? Will it be positive or negative? The derivative of y with respect to z, this direct line, is it going to be positive or negative? Anyone? One person says positive. Siddhartha, why would it be negative? If I increase the z, will this y increase or decrease? What do you guys think? If I increase the z, this z, if this z goes up, will this y increase or decrease? It's going to increase, right? And if I increase this z, what will happen to these y's? Will they increase or decrease? Decrease, right? So basically, that means this derivative will be positive and these derivatives will be negative, right? Anytime, you can work it out. You can just, for those of you who don't believe it, just check it out, right? If I increase the numerator, this term will increase, and to compensate for it, the rest of the terms will decrease, okay? And so when I write out the derivative of the divergence with respect to z, I need this derivative of y with respect to zi. And for the softmax, for the direct line, the derivative of yi with respect to the corresponding zi is simply yi times 1 minus yi. You can see that this is always positive because yi is between 0 and 1. 1 minus yi is also between 0 and 1. This is always positive. And furthermore, it's maximum when yi is close to 0.5. When yi is close to 0 or 1, this becomes close to 0. For all the other terms, because both yi and yj are positive, it's minus of yi yj, so this is actually negative. So the direct derivative is always positive and all the others are negative. And the actual derivative value is proportional to the products of the y's, proportional to each of the y's. So this is what the softmax activation will look like. And so that gives us the update rule for vector activations. And so I can in fact write this whole formula using a Kronecker delta, which says, the derivative with respect to any yj is summing over all. This should be with any zi is summing over all j's of the derivative of with respect to the corresponding yj times yj itself. And this term here, delta will be 1 for the straight line and 0 for the non-straight line. So it's just a simplified notation. But anyway, you get the idea, right? Did the general update rule, the derivative computation rule make sense over here? Yes or no? Okay. What's with the delta? This is just a shorthand notation. If I equals j, this becomes 1. If I is not equal to j, it becomes 0. So this is just my way of using a simple Kronecker delta to determine whether I'm computing the straight derivative, in which case I equals j, or a cross derivative, in which case I is not equal to j, and this becomes 0. That's all. Just a simple notation. But this is the formula. Okay, any questions? Questions, anybody? Okay. So there are some special cases, right? They have some other vector activations there on the slides, but I'm going to look at 2 special cases. Let's look at this guy. A ReLU activation looks like this, right? Is this activation continuous? Is a ReLU continuous? Yes or no? Is it so? Why do you say no? Is there any point where the value changes suddenly? Regardless of whether you're approaching any point from the right or the left, the value at each point is unique. So this is continuous, right? It's not jumping. But is it differentiable everywhere? Is it differentiable? No. At this point, it is not differentiable. So in this case, how will you actually write out the derivative of a function of this kind? So when you have this functions which are non-differentiable in locations, then we have to play some tricks. And so one of the tricks that we like to play is called subderivatives. Remember, we are basically asking what is a derivative? A derivative is saying how much will increase this, perturbing this value, perturb the output. More generally, if you think of it in terms of gradients, you're going to say which is the direction of change which gives me the greatest increase. Now, there's no such thing at discontinuities. So what we can do is basically, we know if I can draw any line which sort of just touches the function over here. And I can use the slope of any of these lines as the derivative at that point. And it's still going to give me a valid value for the derivative as far as gradient descent is concerned. But there's a lot of theory around it. They call it subgradients, subderivatives, cosecants, and so on. But there's a much nicer way of thinking about it. You can think of this as a line which instantaneously rotates from, wait a minute. Why is it like so, right? You can think of this as the line going down, and instead of taking its time to rotate to this point, it's rotating all the way from here to here within an infinitesimal distance. Is this a visualization making sense over here? Is this right? So you can think of it this way, right? Is it making sense to all of you guys? I just got one yes. So Azza, what is the question? What was the doubt over here? What's not clear? So when I have something, when I have a continuous line, right? When I have a continuous line of this kind, the line is changing its direction at each point, and it's changing slowly or fast. But the line is rotating at some point, right? It's going here and then it's rotating. Like if it could rotate slowly, it could rotate fast, it could rotate very fast. Correct? And so you can think of the line as rotating from one point to the other, right? So that means that all of these slopes are occurring at the same point, meaning at that location, any slope value between 0 and 1 is valid. And so for the derivative, you can use any slope value between 0 and 1. They're all equally valid. Typically, we'll use the extremity, we'll use 1. That's for ReLU. Okay, that makes sense so far? Yes or no? Okay. Now, what about the max? There's another derivative called the max. Suppose I have y equals max of, z1, z2, and so on, right? And z3. And specifically, let's say that z3 is the largest value. Then, will perturbing z2 or z1 change y? If z3, so what is the derivative of y with respect to these z's, which are not the maximum? 0, because changing these guys will not change y, correct? But what is the derivative of y with respect to this guy, the one that is the maximum? It's 1. Any change over here directly reflects on 1, right? On y, right? And so for the max activation, which is something that we will often use, the derivative, you have many variables going. One variable comes out, it picks the maximum value. The derivative of y with respect to any z is 0 if it's not the maximum value, and 1 if it's the maximum value. This makes sense? Yes, no? Okay. And so, no, this is perfect. There's no approximation here at all, right? If this guy is not the maximum value, will perturbing it perturb y? Siddhartha. The derivative is 0, right? So, okay, and here is your third pole. And let's see. Fifteen seconds, guys. And okay. Here's what you guys thought. I'll go back. Can somebody tell me the answer? 2, 4, 5, right? Z3 is the maximum value. So the derivative with respect to Z1 and Z2 is going to be 0. And the derivative with respect to Z3 is going to be 1. Perfect. Right. So, okay. And so, the backward pass, these terms, these derivatives may be subgradients, or in the case of the maximum, those two are actually subgradients. So that's the only change that happens. So the overall approach for each data instance, you have a forward pass, you pass the data instance forward through the net, store all intermediate variables, then sweep back through the net and iteratively compute all derivatives with respect to all the weights. The actual loss is the average divergence over all of the training samples. So the derivative of the loss with respect to the network parameters is the average of the derivatives for the individual training instances. These derivatives are computed using backpropagation. Once you compute the derivatives, you can plug them into gradient descent to update your model parameters to decrease the overall loss. So the training by backprop is not training, but it's part of the training process. There's a forward pass where you pass every data instance through the network. There's a backward pass where you compute all the derivatives. You aggregate all the derivatives and compute the weight average derivative, and then update every network parameter by the average derivative of the loss with respect to that parameter. Simple process. So are you good so far with this? Because I'm going to change the way in which we represent everything.
Sir,
Yeah.
sir, where Z is not maximum, it still has some effect on Y, right?
How will it have an effect on Y? Tell me this. If I change this Z, if Z goes from 1 to 2, will Y change?
No, I mean, I'm saying not significantly, but it will, right? Because
Will
it's a
it
vector.
change? Will it change? Just tell me significantly. Just look at this and tell me. If Z becomes 1.2 or 2.8,
No, no,
is there any approximation there?
no.
That's it, right? So where this was the derivative, the transpose of the derivative is the gradient, Aditya. That's why there's a transpose. Okay. The derivative itself. Okay. So now I've just showed you how the math works for individual elements. But we never do it that way. We always think in terms of vectors and vector operations because the arithmetic is much simpler and we have fast matrix libraries to make those things much faster. So we can restate the entire process in vector terms, and this is what is really used in any real system. For this, right? First, consider any layer, right? So I can write all of these y's over here as a vector, a column vector of this kind. I can write all of these z's as another column vector of this kind, okay? Then look at any z. This z is going to be this weight times this y, plus this weight times this y, plus this weight times this y, and so on. So I can write all of these weights as a row. And of course, the y values are written as a column. And so I can also write all of the biases for all of these neurons as a column vector. And so if I actually go back and look at it, I can easily see that if I write all of these y's out, this is y1 through yn, right? Or yd. Then I can say w, say for the second guy, right? W21, W22, W23, and so on. And so this will give me Z2. You can see how this works, right? This making sense? Plus B2, right? And so once I write out all of these weights as a matrix, all the weights going into the ith neuron are the ith row of the matrix. and all the y's become a column, the z's become a column. And so once I write it in this manner, then I can simply write zk equals w subscript over here represents the layer number times yk minus 1, the y's for the previous layer, plus bk. And yk simply applies the activation of the layer to zk. This making sense? Everybody here? Just give me thumbs up. I want to see 50 thumbs up so I can. Very, very straightforward, right? And so once I do this, I can actually write the forward pass very trivially. I can set y0 to be the input. And then the first affine value is simply w1 y0 plus b1, simple matrix operation. And then the next y is simply going to be applying this activation to the z1, which was computed over here. And then the next z is w2, the weights of the second layer times y1 plus b2, the biases for the second layer. And then I can apply the activation for the second layer to z2 and keep doing that till I get all the way to the end and I get the affine terms for the final layer and put it through that activation function to get the output of the network. So the overall arithmetic now looks much, much simpler, much cleaner. When you're writing it in matrix form, I can say y0 equals x. And then within each layer, the z is the weight matrix times the y of the previous layer plus the bias for the layer. And the y for the layer simply applies the activation function of that layer to the z's. And of course, the output of the network is the output of the final layer. Is this pseudocode making sense to you guys? Yes or no? It's very simple. Right? So, okay. Can I get a few more enthusiastic yeses? Okay. Okay. And so here's the forward pass, right? Z equals wy plus b, y equals f of z, period. Very, very trivial when you write it in matrix form. But then you probably get a little, concerned about how do you write derivatives when you're doing things with vectors and matrices. It turns out it's even more simple. And I'm going to, before presenting the backward pass, I'm going to give you some vector calculus first. We are going to use the same notation as we did before. I can still write an influence diagram, z influences y, except I'm no longer specifying z or y to be a scalar. Z can be anything, y can be anything. And this edge contains the derivative of y with respect to z, which I'm representing as this inverted triangle, the nabla zy. Is this making sense? This is still the same notation as before. I've just changed the way that I've just generalized the variables. Now, if y is a scalar, and if z, so if y is a scalar, and a z is a column vector of length n, then what is the shape of this derivative? Anybody? If y is a scalar, rho, it's a row vector of length n, right? And then you can see that nabla zy times delta z equals delta y. And the same equation that we had earlier also holds. Is that making sense to everybody? This one? So give me a thumbs up because I'm going to just build on this and fly. Okay. Now, suppose y is a vector instead of a scalar, right? If y is a vector of this kind. But then I can think of y as a stacking of many scalars, correct? Now, even if y is a vector, I can still write the same thing. Delta y equals the derivative of y with respect to z times delta z. I can still write the same thing, nothing changed. So what happened? Y now is a stacking of scalars, right? Z is still a column vector. So then what can you tell me about this guy? Z is a column vector, right? I've just stacked a bunch of y's. So what will be the term over here that multiplies z? Anybody? What will it be? Want to take a guess? It's a matrix, but what is the matrix? So here, it will be a matrix, but the first entry is going to be the derivative of this y with respect to this z, which is a row vector. The second entry of the matrix is going to be the derivative of this guy with respect to z. The third entry is going to be the derivative. So basically, this derivative is a vertical stacking of the derivatives of these individual y's with respect to z. That's all it is. Does that make sense to you guys? Right. So there's nothing magical about it. It's just over here, if I look at this vectors, then the derivative of y with respect to z, it's called the Jacobian. And the rows of the Jacobian are the derivatives of the individual y's with respect to z. And each row, of course, is going to be, each row is going to have as many components as z itself. And you can still write delta y equals j times delta z. Okay. And of course, if you have, you know, a layer being shown by scalar activations, then you know that the derivative of this y with respect to the remaining z's is going to be 0. So the Jacobian will be a diagonal matrix. Whereas if this is a vector activation, the Jacobian will be a full matrix. But this is in general a generic notation. So this making sense to everybody so far? It's okay. I'm going to fly from here, right? So now look at this again. Suppose I have z equals wy plus b. If I increment y by delta y, what will the corresponding increment in delta z be? If I increment y by delta y, how much will z change? Anybody? And this is simply going to be w times delta y, right? You can just plug it in here. I can say w times y plus delta y plus b is simply z plus w delta y, right? So this is the increment in z. So what this means is that the Jacobian of z with respect to y is going to be w in this particular case. And if I increment b by any small amount, z is going to increase by the exact same amount. So Rishabh, here, again, take a look at this. If I increment y by delta y, so then I'm going to get y plus delta y, right? And w plus b. So if I increment y by delta y, this is going to be the output. Yes or no, Rishabh? Which is the same as wy plus b plus w delta y, correct? Yes or no? Which is z plus w delta y, right? Which is the same as z plus delta z. So in other words, delta z equals w delta y, which means the derivative is, the Jacobian is w. Again, nothing fancy, clear, right? And so also the Jacobian of z with respect to b is an identity matrix. How much ever you perturb b by is how much you perturb z by, okay? And now here's the nested function, right? Suppose I have y equals some function of z, which is some function of x. Then the thing is x influences z, influences y. Each of these edges is going to have the corresponding derivative on top of it. This is exactly like the scalar case. But something important over here, it is the order of multiplication, right? What is if I want to replace this by simply saying x influences y, what is the derivative over here? That derivative is going to be the product of this derivative and this guy, exactly as before, except this term comes first and this term comes second. Otherwise, the sizes won't match. This making sense to you guys? And I will show you why it must be in this order. Okay. And why must it be in this order? Yeah. Check. I know that y, delta y, equals the derivative of y with respect to z times delta z. Delta z equals this derivative, nabla zx times delta x. So plugging this over here, delta y equals delta y, nabla yz times nabla zx times delta x, which means that this guy over here, this term, why is my pencil not showing up? This term here is the derivative of y with respect to x. Right? Can you change the order over here? Will this relationship hold? So that type, if you change the order. Right? So the order is very important. Okay, vector multiplication, the order is important. The dimensions will not fit. Okay, simple. So suppose I have this thing, x influences z influences y influences z influences y influences d. That's right, Eric, the dimensions won't fit. So here's how we can compute the derivatives. I already have the derivative and I put the edges. On each edge, I put the derivative of the destination variable with respect to the source variable. Okay. Then if I want to, I already have the derivative of d with respect to y2 on this edge. Now, if I want to compute the derivative of d with respect to z2, then I just need to consider z, y2, and d. And so going backwards, the derivative of d with respect to z2 is the derivative of d with respect to y2 times the derivative of y2 with respect to z2. This making sense to everybody? Yes, no? Okay. So what is the derivative of d with respect to y1? What will it be? Anyone? What's it going to be? That's simply going to be the derivative of d with respect to z2 times the derivative of z2 with respect to y1, correct? I can simplify this diagram. This has already been computed, right? Is this making sense? Give me a yes or no. We're running out of time, so please be quick. I'd like to see half a dozen yeses at least, okay? Then what will the derivative of d with respect to z1 be? Anyone? What will the derivative of d with respect to z1 be? Somebody? Want to take a guess? Exactly this, right? Derivative of d with respect to y1, which is already computed, right, multiplied by the derivative of y1 with respect to z. All of this works if I'm going to be, if I'm using column vector notation. If I use row vector notation, the orders will change. And then I can take a step back and get the derivative with respect to x as the derivative of d with respect to z times nabla zx, right? And so this is how the chain of derivatives works. And that's what we are going to use. One final thing. Suppose I have z equals wy plus b, and d is a function of z, okay? Then easily enough, the derivative of d with respect to y is the derivative of d with respect to z times the derivative of z with respect to y, which we saw was w. This works, right? The derivative of d with respect to b is the derivative of z with respect to z times the derivative of z with respect to b. But in this case, we already saw that the derivative of z with respect to b is an identity matrix. So the derivative of d with respect to this b is simply the derivative of d with respect to z. So you guys with me on this one? Right. Okay. So Siddhartha, just post that on Piazza and we'll get to this. What is the derivative of d with respect to w? This gets crazy. The derivative of d with respect to this w, it turns out, is y times the derivative of d with respect to z. I'm not going to prove it. We don't have the time, but we can check this very different. Simple. If I have a connection of this kind, the derivative of d with respect to the w here is going to be y times the derivative of d with respect to the z. And let's see how. we know that the derivative of a scalar divergence with respect to an n cross 1 vector is 1 cross n. The derivative of this with respect to an n cross m matrix is its transpose, m cross n. So check this. If this is, guys, I may go a minute over. If this is size m, right? If this is size n, then this is going to be n cross m, right? Because it's going from m to n. So its derivative must be m cross n. The derivative of w must be m cross n. Let's look at this. Y is m cross 1, right? And this guy, which is the derivative of with respect to an n cross 1 vector, is going to be 1 cross n. And so this product is m cross n, which is the correct size. That making sense to everybody? Yes or no? Okay, so you can check. And so here's where we have it, right? I have the derivative of the divergence with respect to B. I have the derivative of the divergence with respect to W. And the derivative of the divergence with respect to Y, once I have this equation. And now everything is good, right? So why did I go over this? Because this basically represents a layer. In any layer, we found Z equals WY plus B. And the divergence, of course, eventually depends on Z. So when you go back, you can apply those rules to compute the derivative of the divergence with, given the derivative of the divergence with respect to Z, we can get the derivative with respect to Y and also both W and B using the rules that we just saw here. And so now let's go back here. Just this, right? The derivative for B is simply the derivative for Z. The derivative for W is simply Y times the derivative for Z. Again, remember this? This will work, right? So this has to do with this simple rule over here. When you have something of this kind, it's Y times the derivative for Z. And now how does this all plug in, right? Actually, let's take this poll and you'll have to spare me a minute because it doesn't take a lot of time afterwards. This is a short poll, only 30 seconds. Ten seconds, guys. All right, let me stop this because I'm running out of time. Anybody want to answer this question? Which one is it? Which one is it? Number 2, right? You have to go outwards. X influences H influences G influences Y. So first, you want the derivative of F with respect to G, the outermost, then the derivative of G with respect to H, the derivative of H with respect to X, left to right, right? This is the correct one. And so here's the backward pass. Here are all the variables. The final y is put through the divergence. I can write this influence diagram like so. X influences Z1, influences Y2, and so on. And I'm using this nabla notation to represent the derivatives. On top of each edge, I can write the local derivative. So this here is the derivative of Z1 with respect to X. This is the derivative of Y1 with respect to Z, and so on, right? And these guys, the derivative of any Y with respect to Z is simply the Jacobian of the activation function. What are the derivatives of Z with respect to Y? Anybody? What are the derivatives of Z with respect to Y? Come on. Just the weights, right? These guys are just the weights of the layer. And so once you have this, it is trivial. You can just compute your derivatives going back. You already have this guy, the derivative for Y. You right multiply it by this Jacobian to get the derivative for Z, right? Which is the Jacobian. Then we have the derivative for Z. Then I can right multiply this by W to get the derivative for Y, right? And then of course, and this is the new term. And then of course, for these weights, it's just Y times the derivative for Z. That's the derivative for this weight. The derivative for this bias is simply the derivative for Z. Then I have the derivative here. I can right multiply that by this Jacobian to get the derivative for this Z. And then I have the derivative there. I can right multiply it by this weight to get the derivative here. And then for these weights, the derivative for this weight is this y times the derivative for this z. And the derivative for the bias is simply the derivative for the z, right? And I keep using this all the way to the beginning of the network. And so here's the simple pseudocode for it. Basically, you just keep right multiplying at each time. So did this make sense? The whole thing. It's very simple. Yes, right. So you start off with the derivative for y. As you keep going back, you keep right multiplying by Jacobians and weights. The derivatives for biases is simply the derivatives for the affine terms. The derivatives for weights is going to be the previous y times the derivative for the affine term. So here's the backward pass pseudocode. So I'll skip the pseudocode, but so here to wrap up then, when I'm setting up for something like digit recognition, you'd be given data of this kind for binary classification, something of this kind for multi-class classification. And you just perform the forward and backward passes, compute derivatives, and update your network parameters. So the story so far, to conclude, neural networks must be trained to minimize the average divergence between the output of the network and the desired output. This is performed using gradient descent. Gradients are computed using backpropagation, which requires a forward pass of inference and backward pass of gradient computation. And these are incorporated into gradient descent, right? And in the next class, we'll look at how well does it learn, how well will it generalize, and what does it really mean. So before I close, can you guys all just let me know if this lecture made sense. You will do so by giving me a thumbs up. And if I get, 100 of these, I got half of you guys. So please. And I'm here for questions. It's not particularly complicated. Let me stop the recording.